Imagine you want to buy 10 paintings for your blank wall and put them up sorted by how much you like each painting. So you go to the painting store and, as luck would have it, they have exactly 10 different paintings, all for the same price. So you take them home, but you're having a hard time deciding how to rank them so you can put them up in that order. When you look at any two paintings, you can easily decide which one you like the best, but how do you turn that intuition into a complete list ranking every painting? One obvious answer is to compare every painting with every other painting. The one that compared better against all other paintings must be the one you like the best, and the one that compared better against every other painting than the best one must be the second best, and so on. That seems to work. So we have to compare every painting to every other painting. That's 10 times 10 equals 100 comparisons, right? Wait, look at all these places. We don't need to compare something against itself. And notice how every comparison is actually repeated twice, but with the two paintings swapped, which gives us this symmetry line down the diagonal. If we remove all of those, we're left with just 45 comparisons. We can find a generalized expression for this just by retracing our steps. We squared the number of paintings, but then we subtracted one comparison for every painting, since they don't need to be compared to themselves. Finally, we cut that number in half by removing duplicates. Okay, let's use our newfound ranking algorithm in another situation. We'll try ranking our marble collection of 400 marbles. Let's see, 400 squared minus 400 divided by 2, and that's 79,800 comparisons. Yikes, that's not so good. Wait, I got an idea. Suppose I figure out that I like marble A better than marble B, and I also discover that I like marble B better than marble C. It seems there's a shortcut here. Presumably, we can already tell that I'm going to like marble A better than marble C, since A already compared better than B, which we also know is better than C. So we just removed a comparison that we otherwise needed to do. I think there's a lot of comparisons we can remove this way, which might make it feasible to rank all 400 marbles. Let's go back and see what this shortcut can do to the paintings. First of all, as we established before, we don't need to compare paintings against themselves, and we can also remove duplicate comparisons. Now, if I compare A and B and figure out that A is better, and I compare B and C and figure out B is better, we can eliminate this comparison between A and C. Next up is D. If I compare it to B and find out it's worse, I don't need to compare it to A. I can compare it to C, and let's say it's worse again. Finally, let's look at E. Comparing it to C, we can see it's worse. But since C is worse than both B and A, we don't have to compare E to any of those. Now, for the sake of simplicity, let's assume that the letters continue to correspond to how much we like them. Filling in the rest of the table, it ends up looking like this. We only have 19 comparisons remaining. That's pretty good. Remember that we started thinking we had to do 100 comparisons. I still feel like there's a bit of intuition missing here though. How do you know which comparisons to actually perform? I mean, ideally, we want to remove as many comparisons as possible with every comparison we do. And if we figure out that a painting is worse than another painting, we can remove comparisons to paintings we already know are better than the one we compared it to. In other words, what we do is we keep a working ranked list. We do the first comparison and add the two paintings to the ranking list. Then we take a new candidate, compare it to one of them, and already we might be able to remove a comparison and add it to the ranking list. What we do is we always compare new candidates to the element in the middle of the ranking list. Since no matter if it's better or worse, we'll remove the need to compare to the bottom or top half of the already ranked elements. You can really see this when we add the final painting to the ranking list. There's 9 paintings, so we compare it to the middle one. Let's say it's worse. We now also know it's going to be worse than the top 4, so we strike those. There's now 4 paintings remaining, and we could compare to the middle one of those. If there's an even number of remaining paintings, we might have to just choose one. If it's worse again, we strike the top half and compare against the only remaining element, and since it's going to be worse again, we can place it at the bottom. We did that with only 3 comparisons instead of 9 by using each comparison to cut the list in half. Now, so far I've been sorting paintings according to the letters of the alphabet when they were already sorted in that order, which kind of doesn't make much sense. So, it might have been tempting to think that we could have just jumped directly to the bottom of the list and compared it there. But in a real-world scenario with random data, you don't know ahead of time if the painting belongs above or below the element you're comparing to. Let me show a different example to illustrate this. Now we've ranked 9 elements so far, and by chance, the last painting to rank is C. It's greater than F, so this time we eliminate the bottom half comparisons. Now we compare to the halfway point of the remaining paintings, which is D. C is still greater, so we don't have to compare against E. We then compare against B. C is smaller, and since no comparisons remain below D, we know that's where to put C. So now we know how this algorithm works in theory. Let's go back to this table. With the first, more naive technique, we could easily see how to calculate the amount of comparisons needed to produce the ranking list. It's a bit trickier to do with this one, but one way to look at it is, when we have X paintings already ranked, how many times must we cut that list in half to know where to place the new painting? As we saw before, for 9 paintings, that number is 3. It's like an inverse exponential. Instead of what number do I get if I keep doubling this number, it's how many times must I have this number to get back to 1. That function, as you may already have heard of, is called a logarithm. Specifically, the base 2 logarithm, since we're dividing by 2 every time. Now, we can actually plot this function on a graph. It looks like this. You can see that when you want to rank only one element, it takes 0 comparisons, since that element is the whole list. And when it's 2 elements, it takes only 1 comparison. And as we saw before, when we have 9 elements, it takes just about 3 comparisons. Oh, but of course, we want to know the total number of comparisons to go from an empty list to have ranked all 10 paintings. To do that, we just have to find the area under this curve. It makes sense if you think about it, since the value of the function at each whole number corresponds to the amount of comparisons required to place that specific painting on the working ranking list. And finding the area under the curve, also known as the integral, is equivalent to just adding up those numbers, but in a more precise, mathy way. To give an example, the integral of this function between 1 and 10 is about 20, which is close to the 19 we showed earlier. The exact amount can vary depending on how the paintings were shuffled when we started ordering them. Now, the integral between 1 and any number n looks like this. In other words, to see how many comparisons we need to do in order to rank n elements, we just plop that number into this expression here. So, for our 400 marbles example, instead of 79,800 comparisons, we only need to do 2,882 comparisons. You can see how this works when we zoom out from the graph. The number of comparisons needed to place every subsequent element grows very, very slowly, instead of exponentially like our original formula did. Hopefully it's clear by now how you would rank 400 marbles using this technique. Always start in the middle and compare. If it's worse, eliminate the top half. If it's better, eliminate the bottom half. Now keep doing that until all comparisons have been eliminated or performed, and that last comparison will tell you if the new marble should be just below or just above that last marble you compared it to. In other words, you're searching for the correct place to put this new marble into the working ranking list. The algorithm we've just stumbled upon is called binary search. Binary because we keep splitting up the list in 2. It can work for both finding the correct spot in a sorted list to insert a new element, but also the other way around if we want to find an element in a sorted list and don't want to scan through and examine every element in the list. It's the way you might find a word you're looking for in an old-fashioned dictionary. This is really useful for computers when looking up data in a really long list where checking every element to see if it's the one it's looking for can be really costly. Of course, if we knew an actual affection score for every painting or marble describing how much you liked it, we could just tell a computer to sort it using, well, any sorting algorithm really, and it would be much faster than asking a human to compare them. What we're doing is assuming that each painting has an intrinsic affection score, but that we just don't know what it is. We imagine that a list of the paintings sorted by how much we like them theoretically exists, and we're trying to find where in this list each painting belongs by using binary search, because search and sorting algorithms don't need to know the absolute values we're ordering by. They just need to know how any 2 elements compare. So, can such a theoretical list always exist? Let's try something. Which is better, rock or scissors? Well, rock beats scissors, so let's go with that. Okay, which is better, scissors or paper? Now, scissors beats paper. Okay, the list is done. Rock is better than both scissors and paper, so I guess we'll just always throw rock when playing rock, paper, scissors? Wait, what went wrong here? Think back to 1,542 words ago when I said, presumably, we can already tell that I'm going to like marble A better than C, since A already compared better than B, which we know is better than C. That first word wasn't an accident. That was an assumption. We assumed that the list of elements was transitive. That's the mathematical way of saying exactly that. When A is greater than B and B is greater than C, A must also be greater than C. But rock, paper, scissors is a classic example of a non-transitive game, that is, no move is better than all other moves. You can't sort or rank the moves by how intrinsically well they perform in the game. So, I hope our preference for the paintings is transitive. It's difficult to say whether or not that's the case, because the problem is inherently subjective. If there was an objective factor involved, we could just feed that to a computer and it would sort it for us. But there's no absolute value we can assign to how much we like something, it's all relative. The problem fundamentally requires a human to compare paintings, but there's no guarantee that all painting pairs will be judged on the same criteria. For one pair, you might prefer one of them for the painting style. Another pair, you might prefer one for the colors used. And that's not even mentioning factors like monetary value or the reputation of the artist who painted it. So when using a shortcut like binary search, you do risk getting an inaccurate picture of the actual ranking, and maybe you want to go back and revise the ranking list afterwards, but I still think this algorithm gives a very good starting point for a ranking list, especially considering the massive time save it can provide. That's why I've made a small web page at oneero.com/binaryrank, which can be used to sort data exactly like this. You can input the data to sort in two formats, CSV and JSON, and you then just click away, telling the site which of two things you like better. The data and ranking list is encoded in the URL of the page, so you can save it and come back and continue later, or you can even share it to show off your ranking to someone else. I hope this video helped give an intuition for how a ranking system like this works. And if you ever need to rank a long list of things, now you know how to do it.